To see such a full crowd for our speaker today. This is another installment in the Coughlin lecture series. In fact, the namesake, Claire Coughlin, is here today, the founding member of this department, and I think of this college, as I understand. It doesn't like me to point out such things that date them like that. Permit me to read to you. For over 30 years, Gary Rockswold has taught mathematics, computer science, and physical science at a wide variety of levels, including high school, undergraduate, and graduate students. He received his bachelor's degree from St. Olaf College and his PhD in applied mathematics from Iowa State University. He's been a principal investigator at the Minnesota Supercomputer Institute and is an emeritus professor of mathematics at Minnesota State University, Mankato. He's an author and has published several mathematics textbooks for Pearson Education at both the developmental and pre-calculus levels. And he's also a member of my oral exam committee, one of 3 people that were subjected to hearing that before dinner one night back in 1985. So if you're just joining us, see if you can find a seat. If not, please file along the sides and back of the room. So with that, I ask you to welcome Professor Gary Rockswold.
There's a few seats. You don't have to, I think there are a few chairs unless you really want to stand. There's a seat over there. I see one here. There's a little bit. You probably want to sit down. Relax. I assume a lot of you students here. Maybe you're required to be here. I know. Sure. That doesn't. I don't know if you're a group of volunteers or not. But anyway, I just want to thank you all for coming. It's really a pleasure to be here. Have a chance to talk about this. This is a. If you came to learn how to add fractions, this isn't the talk. Okay, we're not going to talk about that kind of stuff. The intent for this presentation goes back to a little bit how math is done here. I'm just going to wait just a second here. And that is, in mathematics, and you know as a student, that you spend a lot of times with details. Right? There's just a lot of time with the details. And, in all honesty, it's important where the decimal point goes, particularly when it's your paycheck or something like that. I mean, you'd like to have that done right. And so mathematics has a lot of details in it. And as teachers, we teach, there's a lot of stuff, and you maybe feel this way as a student, if you're taking calc or whatever it is, man, there's a lot of material every day they pour down. And we spend a lot of time with the details. Mathematicians are pretty good on the details, and they spend a lot of time on that. And what I would like to talk about today is more of the big picture. Why do we do it? Why is it important? And I want to talk a little bit more about, instead of looking at the trees, I want to look at the forest. I want to just look at the big view. And really, there's a real disconnect with the public and mathematics. Maybe there's a disconnect with the students in mathematics or whatever. And I would like to just talk a little bit about what's happening in math and some of the things I think about mathematics. Now, do students believe the math? Maybe you don't. Often they think it makes their lives more complicated. But actually, there's a quote here: the essence of mathematics is not to make simple things complicated, but to make complicated things simple. Ideally, that's what we'd like to do. May not always seem like it if you're a student. Do we believe the math? Well, sometimes we think it's actually, might think it's a waste of time, but actually, math makes life easier. The human mind has never invented a labor-saving device greater than algebra. Now, the thing is about this is, if you think about it, if you know the mathematics, you only have to cut the board once, you only have to make the bridge once, and it won't fall down. Mathematics is amazing in that, in that you can design something ahead of time, whether it's an airplane wing, you don't need to drag it in the wind tunnel all the time. The modeling of mathematics will make it right, and you see that even with the 35W bridge. It fell down because the plates were, what, about half as thick as they're supposed to be, was one reason anyway. So math, when you think about it, you only have to build something once if you do the math. So it does save a lot of time. You don't have to let it fall down and say, oh, okay, I got to do that, I got to do this, and then let it fall down and do it again. Giving meaning to the math. Math is meaningful, and it's important to show how it relates to people's lives. Now, one thing here, you probably have seen Venn diagrams, I'm sure everybody is here, and you know it's kind of common, you know, to say, okay, that's the algebra student, that's the trig student, what's the green? People taking algebra and trig, right? Okay, well, there's another way you can look at it. You can say, well, that's people wearing sandals. That's people wearing socks, right? And who's in the middle? You ask the student, it'll probably say, my dad, right? Good news for mathematics reading. The Late Late Show, I don't know if any of you watched that or not. Craig Kilborn comes out and says, it's a great day for America. And one thing that it really is, I think, it's really a great day for mathematics, and what's happening in math and what's going to happen in the future. Best and worst jobs. Wall Street Journal always comes out with this. This is just a year or so ago, and they have 5 criterion on saying what's the best job and the worst job. Well, the results are, I don't know if you can guess the worst job. Lumberjack. And you know, when you think about it, it's pretty stressful and dangerous and cold, and they yell at each other. If you've seen Discovery Channel, and they swear and all that. I mean, it's not ideal, I wouldn't think. But the best job a few years ago had to do with mathematician, and if nothing else, usually the occupation has to do with mathematics. Okay, it might be stat, it might be comp sci, and this is, I don't know if you noticed this here. They got the little smug professor up here doing all his equals, smiley face, and then the lumberjack has his little sad face down there or whatever. I don't know. Transforming concepts. Certainly the internet has transformed, and as a student, maybe you've seen movies like The Matrix. It's getting a little old now, but that was sort of a reality that was created by within a matrix. Now, most of us don't realize that matrices are really creating this virtual reality called the internet. And how is that happening? Well, you can take, let's take this as a little web, very small web page. Okay, this is a web page, and this is a link. So I can go from 1 to 2 on a click. Okay, I can, if I'm on web page 3, I can click and get to 2, or I can get to 4, and so on and so forth. So obviously this is very small, very simple. All right. So we can model a web in this way, and then we can take, I don't know if you study matrices or not, but we can take something called an adjacency matrix. And then what we can do is we can say, well, we got this one here from 1 to 2. So in slot row 1, column 2, we put a 1. That means I can get there from it, and so on and so forth. So like 3 can go to 2 and 4, so 3 can go to column 2, column 4. Okay? So we got a path there. So now we have it in a matrix. Well, once you can put it into mathematical form, now you have something. Well, what can we do with it? Well, we can calculate possible lengths. I don't know if you've ever wondered why in the world would you ever want to multiply 2 matrices. Well, we can actually, I'll show you here, if we compute a times a squared, that'll tell us if we can get from web page I to j in 2 clicks. If it's a cubed, can we get there in 3 clicks, and so on and so forth. So let's just take a look at this, how this works. All right, so here's a squared, okay, and here's the result. And then let's take this, now, if we take this one here, there is one path of length 2 clicks. This is in 3.1, okay, from web page 3 to 1. So I can get to from 3 to 1 in 2 clicks. I can also get here, what, 4 to 2 in 2 clicks, because there's a 1 there. Okay? And then you can do a cubed and so on with it. Size of the internet. Well, of course, there's, I don't know, order of 30 billion web pages or whatever out there, and it's growing. And the following graph, I thought they did a nice job on this. This is 6,400 vertices and 13,000 edges. Now, this is the power of visualization, really, and it's something that's really important. And in some ways, I wish we did more geometry where you visualize stuff. But if you're, look, if you want to advertise somewhere, what? You don't advertise out on this guy's webpage, right? Because nobody's looking there. You want to be in here. You want to see an endpoint to your webpage if you can be able to go that way. Social networks. Well, mathematics and the media. You probably had, a lot of you got CEO of Slide, Max Levchin. He made a comment about his success as far as writing applications for like Facebook and places like that. He said the following: our competitive advantage is actually our math skills, which is probably not something you'd expect from a media company. And it's very interesting, but there's a tendency to think, I'm not a STEM student. I'm not in science, technology, engineering, mathematics. I'm going to go to media, or I'm going to go somewhere else. But why is Google so good? They just went over 1,000 a share, by the way. I wish I would have bought some right a while back. But why is Google? They got the best mathematicians. That's part of the reason. That is, being able to search that many items in a fraction of a second is extremely mathematical. It has a lot of mathematics behind it. So math skills, I think more and more, it used to be, well, what are you going into? Well, I'm not going into physics, I'm not going into math and some stuff. I'm going to go into, I don't know, psych, bio, whatever. And therefore I don't need to take math. But what's happening more and more is there's more math requirements, and there's more people having to take math, and somehow we need to teach it better, and we also need to learn it better, really. Social networks and directed graphs. Okay, now let's take this is social network, this is friendship, let's say like, okay? So, person 1 and 2 are friends. Okay? It looks like 5 and 4 are friends. Okay? 5 likes 1. I don't know, 1 doesn't like 5, I guess. And like 3 likes everybody, right? But nobody likes 3. We've all met 3, right? I mean, really. You know? Okay, so you get the idea. Again, we have a diagram, so immediately then what one can do is you can slap it into adjacency matrix. So we'll take it and we'll put it in an adjacency matrix here. And so now we can start to see information here. And for instance, see like a lot of people like 1, evidently. And here 3 likes a lot of people, but nobody likes 3. I don't know, nobody likes himself. I don't know, that's a different thing. You could weight it also on the diagonal. Structure, okay, so I kind of went through this. Symmetry, for instance, here. What does symmetry mean? All of a sudden we got a mathematical form. Well, we got symmetry going on here, but that is 1 and 2, and so they like each other. 3 and 4 like each other, but there isn't much else for symmetry in there. So symmetry tells you something. Row sums tell you something, and column sums tell you something then. Just by looking at the matrix, you can tell something about the social network system. Now, all this social stuff, how they're hunting this down, this is getting very highly skilled where they figure out where, you hear where they say they can just look at your Facebook friends, not even your page, and tell a lot about you. And it's key for advertisement. So rather than doing a 30-second commercial on the Super Bowl, they'll target through all of this social media type stuff. So calculating social distance here. Well, a squared, we can calculate that. Well, what does this mean? Let's take a look at this 3 here when we do a. That means I can go 3 to 1 with social distance 2. So I can go 3, 2, 1, that's 1 time. 3, 4, 1, that's 2 times. 3, 5, 1, that's 3 times. So that's social distance. And that might be meaningful if, let's say you want to start a rumor, who are you going to give it to? Oh, maybe 3, right? I mean, you just want to get it out there. Essence of mathematics. One profound concept, there's a lot of essence of mathematics. I don't claim to know the essence of mathematics, but one profound concept can be used to simplify a vast array of complicated problems. So, for instance, with this matrix thing, we did social networks, we did internet. Some of you may have done transportation problems. I'm not sure where you're at with that, but you can do them with matrices, internet pages and links, and social networks. Modeling non-rational choice. There's a tendency to think that you can only model rational things with math. They actually try to do it non-rational stuff also with this. So for instance, losses and gains. Here's quiz time. Is it better to give your significant other 2 $100 presents or 1 $200 present?
Both.
That's plain and safe. I agree with that.
Depends on how much messed up.
Okay, another one. If a person wins $50 and gets a $25 parking ticket, are they happy? Right? There's something about it, right? Okay, well, economists spend a lot of time on this type of stuff, but behavior and losses. People weigh losses significantly more than they do gains, about double. People are loss-adverse behavior, they demonstrate that. And the somewhat non-rational behavior is modeled by the following value function. So, if we model it here, just to talk about this a little bit, if we have, let's take that first one, $200 presents versus a 200. Okay, how this works here, we'll make it really simple. This is money on the x-axis, so this is you gain money, this is you lose money, and this is, it makes me feel happy, makes me feel sad type idea. Pretty loose here, but the idea is this. Okay, if you get a $200 gift, say you're out here, you go up, and you're over, and they're happy. What's not to be happy about, right? Okay, but the idea of a 100 is half the distance, but because of what? The concavity of it, I'm happy, and I'm happy again. And I don't know if any of you have, when you got little kids, you don't give them one present at Christmas, right? You give them a bunch of little ones, and it seems to make them happier. Now, if you take, for instance, the parking ticket and the $50. Well, I win $50, so I'm happy. But because this is not what? It's not symmetric. It's not an odd. You can't rotate it and make it symmetric. You go over 25, and it's almost a wash. Is what they'll come up with. Now, are people rational? Well, people's value functions are typically concave. Now, if people were totally rational on this, what would you have for a graph? Straight line to the origin, right? And then what you did, it would be linear, and then you'd have the slope could kind of be the excitability factor, right? So if they really get hyped up over gifts, they'd have a real steep slope, and if they don't really, they're kind of deadpan, they don't care, you'd have more of a horizontal slope with it. This is a little clip I'm going to do here, and it has to do with what they're doing with social media. and how science and math is starting to get into this social media type stuff. It's just, the clips I show here, they're just like a couple minutes long.
I have a background in math, physics, electrical engineering, but I've spent a lot of time also in the social sciences as well. Understanding how large groups function, we've of course been worried about how we should run society forever, really. We've moved to an age where people are connected online. People can communicate at incredible rates with all sorts of people. They can digest and move information around. It's unparalleled. It's crucial that we understand it from a basic science point of view. What happens when you connect people in different types of networks, for example? Will they produce a good outcome, a biased outcome? And some of our work in particular then is looking at emotions, how emotions spread, the contagion of emotion, if you like. There's one site in particular, WeFeelFine.org, that we've been harvesting data from. They, of course, in turn have been harvesting data from blogs. Any sentence that starts with I feel or I am feeling, they pull that off a blog, and then you have a timestamp, and in some cases you have the age of the blogger and where they live. So you have this demographic data, which is very important. And we've been able to find out a number of things, because now we're watching what people do. We're not asking them how they feel. We're watching how they express themselves. This is really getting at a fundamental problem for measuring how well society is doing. Right? We're not used to understanding how 100,000 people will behave. There is a transition, I think, in the social sciences where you move away from just having ideas, abstract ideas about how society should function, how an economic system should function. We can go and look. Now we can go and look. We just did not have that data before.
You know, there's really a point there, and that is that the social sciences are starting to get more mathematical. I never thought they would model the contagion of emotion. You know what I mean? If you caught that in there, I mean, how do you do that? But that's what they're starting to do with this. And the other thing is that because I know there's going to be a distraction here. The thing is now they're actually dealing with what people are doing. It's not a view or a I'm taking a survey here. They're actually doing what it is. I know. Now some of you are thinking this whole thing is going to start to really digress here. This is a theorem from topology. And what it says really is a sphere is completely covered. If a sphere is completely covered in hair, then those hairs cannot be made to lie flat without having a cowlick. Okay? I remember I first saw that I thought, no way, and will there ever be an application of this? Well, it turns out that would anyone use this, it turned out that some people from MIT used it to justify keeping nanoparticles to stick together. So it actually ended up having an application for it. Now one thing when you apply a theorem, and that is that the hair, it doesn't apply to a comb over, because the hair has to completely cover the ball. So he doesn't have to have a cowlick that way, I guess. Making connections in life. Gotta always have a puppy, they're cute, right? You probably know this. You have a small animal will burn calories faster than a big animal, for instance, like an elephant or whatever. It burns it at a faster rate, right? A small one will. Now, it had been really a mystery for a very long time for people to figure out, well, if it was based on the surface area. The elephant has more surface area but it's based on the 2/3 power. It's not linear is what I'm saying, so if you are inversely linear where you double the size of the animal, then the rate is half as much. They couldn't figure it out. It actually ended up being based on the 3/4 exponent. And so this was kind of a x to the 3/4. A problem with it. Well, it turned out that fractals can generate things with a 3/4 power. And what I mean by this is it turns out like a tree, if you cut a branch, you got another tree, only it's a small tree, cut it, another small tree. Circulatory system is a little bit that way also. Turns out people, animals, all of that follows it, and with a little bit of mathematics they were able to use fractals to show that, yeah, it should be the 3/4 power. There's no branch of mathematics, however abstract, which may not someday be applied to the real world. This was, I don't know if you've taken Lobachevsky, if you've ever taken non-Euclidean geometry, some of you probably don't have if you're, if you're sophomores. That's usually like when you're a junior or senior if you happen to go into that stuff. But it's, there's vectors. Maybe you've understood trying to understand the world. When scientists were trying to understand electricity originally, it was an industrial revolution. So they were using gears and pulleys to do everything. And so if they were going to try to figure out what electricity was going to do, they said, well, we'll try to explain it with gears and pulleys and wheels and stuff like that. Well, it was too hard. It didn't work. Well, once things are too hard, you try to come up with another model. Try to come up with something different. So vectors ended up being the solution. I don't know how many, again, I'm not sure where you're at here. If you're in calc, maybe you had, but the idea of a vector, forces pulling on ropes, for instance, you could solve with vectors. You could also solve things like electricity and magnetism. Ended up being vectors. In fact, it appears the whole world is field theory, is vectors. Somebody had good timing there. I don't know if they get that shot there, that hitting that tree. The essence of mathematics. One mathematical concept was able to solve a large number of problems. So you have like the idea of just a simple idea, like, I don't know if you've had this before, but a force, you pull on a rope this way, pull on a rope this way. This is the direction that the force is, and the length has to do with how hard it's being pulled. In other words, you could pull one just this way, or both these would be equivalent to this. And if the wind is the same way, if the airplane is flying this way at this speed, this airplane flying this way, this is the wind, this is the way the airplane's going to go. It's amazing that something that simple works for so many things. Dimensions. More dimensions than 3. Way back when, they used to think there's only 3 dimensions. Euclid said, look, it's obvious. Left, right, forward, back, up, down, there's nothing more. That was sort of the proof of it. Well, it turns out they're starting in 1854, Riemann. I don't know if you had Calc 1, you maybe, or 2, you might be doing some Riemann sums, I don't know, or at the end of it. But he was a student of Gauss, who was a famous mathematician, and he was going to do on n-dimensional geometry, that you could do all this math in not just 3, but 4 or 5 dimensions, because the math could work. And Riemann was really a nervous student. And the first time he was supposed to give it, he got all nervous, threw up, and didn't show up, and then the next time, and you got to admit, it's interesting because Riemann was a genius, obviously, and the point is, everybody can get a little nervous about talking about math or taking a test or whatever it is. It's pretty innate. Well, he came out with it, and this ended up being a really important lecture. In fact, afterwards, after he gave it, then everybody got involved, and they thought, oh, there's 4th dimension, and that must be where ghosts are, and the church got involved, and all the spiritual world, and all of this stuff started to happen after this, but it was a very important lecture. And as we know, Einstein picked it up and used the 4th dimension to be time. You know, you probably have heard that a little bit. That became the fourth dimension. Einstein used a lot of Riemann's work. Math provides a concept. Without mathematics, the concept of higher dimension is impossible. Nobody can think in higher dimensions. They tell you they can, they can't. I mean, you can't really picture in 4 dimensions. I've seen people try to draw it on a 2-dimensional blackboard, but I don't believe it. And now physicists, this is where it gets weird, because now physicists are starting to use these higher dimensions, the concept of higher dimensions, to explain why gravity is weak. And what do I mean by that? Okay, you got the big Earth here, right? Huge. And then you take a paper clip, you take a little magnet, and the magnet picks up the paper clip and wins out over the gravity, right? And then you take some little pieces of paper, you maybe did this in elementary school, you probably don't do it too much, and you comb your hair with a little comb, get some static electricity, and you pick up the paper, right? And so what? The electrical force is stronger than the gravity. You've got the whole big Earth underneath that's trying to pull that paper down, can't do it. Okay, so then they're thinking, well, why is that? Why should gravity be so much weaker? Well, then they start to think about dimensions, and if you've got higher dimensions, you've got more universes, you've got all kinds of stuff. This next little clip has to do with that, and it talks a little bit about higher dimensions.
It turns out that there are very new ideas on how to explain the weakness of gravity if we have extra dimensions.
When M theory emerged, Randall and her colleagues wondered if it might provide the explanation. Could gravity be leaking from our universe into the empty space of the 11th dimension?
Gravity might only appear to be weak, even though it's fundamentally just as strong as everything else, because it dilutes its strength out in all these extra dimensions that we can't see.
Randall tried to calculate how gravity could leak from our membrane universe into empty space, but she couldn't make it work. Then she heard the theory that there might be another membrane in the 11th dimension. Now she had a really strange thought. What if gravity wasn't leaking from our universe, but to it? What if it came from that other universe? On that membrane, or brain, gravity would be as strong as the other forces. But by the time it reached us, it would only be a faint signal. Now, when she reworked her calculations, everything fitted exactly.
The thing I think that's a little strange about this, or whatever you want to call it, is nobody's seen 11 dimensions. But there's a lot of people in string theory and physics that are working with 11 dimensions. Well, why are they doing that? Well, it turns out the mathematics works in it. And you might say, if you have a theory in physics, and you can't make the math stick with it, it's not a good theory. It's just the way it seems to work. And you might say, well, yeah, I don't know why, that seems kind of magical. I mean, why is that? Well, even if you go back to not believing the math, Einstein, this happened to Einstein. Einstein did relativity, which I'm sure you've heard of. And his equation said that the universe should be expanding. Okay? But at that time, everybody thought the universe was static. It wasn't getting bigger, it wasn't getting smaller, it was the same. And so what he did to his equations is he put in the cosmological constant, which if you guys have taken it in the lab, is called a fudge factor. Okay? He put in this extra thing to make it static. All right, well, what happened then? Well, in 1929, Hubble experimentally showed that the galaxies are moving away from us. And Einstein was already really famous by this time, and he could have been even more. This would have been bigger than anything to be able to predict this. But he kind of choked on it and said no. And so what Einstein did in 31 is he dropped it and said it was the biggest blunder of his life. And And so in a way, that was a case where someone did not believe the math. You know, the logic tells me, no, that shouldn't be that case. I don't know how many of you heard about the Large Hadron Collider. It's good. It's an atom smasher, okay? And it's in Geneva. And this is like 27 kilometers around here, okay? And it's like 100 or more meters deep, and so that things don't interfere with the cosmic rays and stuff like that. And so they got these. They're trying to accelerate. We were gonna try to build one in Texas along in the early 90s or whatever, but it got canned and that. But anyway, they did it. They got it set up and going. And the idea was to get protons are heavier than electrons and get them going and smash them together and see what happens. And you say, well, why do you want to do that? Well, this is a picture from underneath here. What that? And this goes around. That's down there. And why did they build it? Well, I've read articles, and one is, in one word, Higgs. They're looking for the Higgs particle.
The God particle.
Yep, sometimes called the God particle. And what does that have to do with? All right, why do they want to find it? Well, it gives the universe mass. It's the concept of mass. It's a bit of a mystery. When you hop in your car and you step on the foot peak, why do you get pushed back in the seat? I mean, who's pushing you, right? I mean, and you can do this out in the middle of space, you know what I mean, in a rocket, and you'll get pushed back. It's kind of everywhere, but there's no real, I mean, you call it inertia. Newton called it inertia, but what is that, you know? There's, you know, everything else has a particle to it. Light has a photon, gravity has a graviton, you know, electron, things like this. So they're going to look for this, but it's really heavy. Now, well, why do they believe, at that time, in 2008, there's no experimental evidence for the Higgs particle. So why are they going to build $1 billion atom smasher if they don't have any experimental evidence for this? Well, it turns out, interestingly enough, that in 1964, Peter Higgs proposed the Higgs particle, he didn't call it that, in a paper that contained only 79 lines and 5 equations. And he said, look, with symmetry, physicists believe in symmetry, and with symmetry, all the equations are going to look better if we got this particle. The equations sort of hinted at that this particle should exist. Well, turns out that they found it. So, you know, we're just like fish have discovered there's water here. And I don't know if you understand that. What I'm saying here is that if you think, imagine yourself, you're a fish, and you're in water, and you try to swim fast, and what happens? The water pushes back at you, right? Slows you down. Does the fish know there's water there? Or, you know, and it's a little bit the same way. What's slowing us down when we want to try to accelerate? Well, it turns out that evidently there is a particle for it, and it's called the Higgs particle, and empty space is not empty, because it's everywhere. Another stir they had is they went on, when they were doing this collider, they said, oh, in this collider, this is going to be wonderful. We're going to make black holes in this. We're hopeful of making black holes. And the public said, no, we don't want black holes, okay? Look, you know, if there's a black hole there that way, you know, if you watch old Star Trek, you know, you tell Scotty to gun it and go that way, right? Black holes get bigger, they suck things in, bad things happen around black holes. And so the whole idea of them making black holes in this collider was like, no, you know, we don't want that. And so then they had to backtrack and explain a little bit. Well, it turns out that Stephen Hawking showed mathematically that tiny black holes will disintegrate in a matter of a few fractions of a second. Oh, that makes me comfortable. I mean, think about it now. Okay, so he mathematically showed that this had to happen, but nobody's made a black hole, nobody's really tested this, but they're going to go ahead and do it anyway. And the only conclusion I can get out of that is that scientists really do trust mathematics. At some level, they have to, right? You know, and I think sometimes math, it's a little bit of an unsung hero behind some of this. engineers are really good at saying they can do anything. You know, mathematicians are kind of, well, we can't, you know, I'm pretty specialized here. They tend not to talk about their field as much. But it really is an unsung hero. Mathematics can lead us in a direction we would not take if we only followed up on the physical ideas themselves. And this guy won a Nobel Prize, and he predicted antimatter in 1928 with his equations, and then they discovered it in 1932. Well, sometimes in life, you see what you look for, right? I mean, you see in life what you look for, and if an equation tells you to look for this, you got a better chance of seeing it. Okay, this is my attempt. You know how you have like a Super Bowl, you know, before it they have the football players catching and then the passes and rolling into the end zone, and they play music to it, and everything looks better when you know, rock stars, whatever, when you have music with it. So this is my attempt to put music to math, all right? And this is, I just call this the essence of mathematics. You'll get the idea of it as I play it here. And it's just some ideas with it. So I hope you enjoy this one. I'd like to kind of work towards the end of this here with just talking about some open questions and some ideas here. It's interesting, why does the world organize itself so you can even be described by mathematics? You know, like some of you have taken a little physics, force equals mass times acceleration. I mean, it's so simple too. Why should something that simple work? You take another open question. Why is math able to make predictions? So you have like E equals MC squared. All of you have heard of that. Well, why isn't it E equals MC to the 2.145, you know, or something? You know, why is it just squared? And how is it that we can use that to predict that there is nuclear energy, and we understand then how the sun works? You know, that the E equals MC squared came before we understood that. that whole concept of nuclear energy. Equations often come before observation, which is a little, in my mind at least, a little bit of a mystery. I mean, we always think of form as preceding thought. But can thought precede form? I mean, in a certain sense, we tell each other, follow your dreams. You got to have a dream or it'll never happen. That's sort of thought preceding form. Galileo said this, and the Book of Nature is written in the language of mathematics. 1642, it was right before Newton was born. Pretty amazing that he could see that, understanding the universe. The smallest units of matter are not physical objects in the ordinary sense. This is like an electron or a photon. They are forms, ideas which can be expressed unambiguously only in the mathematical language. So they're almost mathematical entities then. They're finding. This was done, some of you have heard of Heisenberg. There's another one here, the unreasonable effectiveness of mathematics and the natural scientists. He was a Nobel Prize winner, a very interesting guy. It's an interesting paper. It's not overly complicated at all. And then to show you how far it's come, there's Max Tegmark, which you'll see on the Science Channel once in a while. You know, it's a little like Brian Greene. You'll see him around also. And he came out with this statement here, which is, I mean, to the normal person, including myself, sounds a little strange, but it shows you how far the mathematics is moving in our world. He said, physical reality is a mathematical structure, and our universe is not just described by mathematics, it is mathematics. I don't know if that's true or not, but the point is, you can see how far it's coming. It's playing a bigger and bigger role. Mathematics is transforming. It's really more than a tool. There's a tendency to say, well, I'm going to be a physicist, so therefore I got to learn mathematics. I'm going to do computer science, so therefore I got to know discrete math. It's kind of like a carpenter needs a hammer, but a hammer doesn't really tell you how to build a house, but mathematics does. Mathematics has a certain creative element to it, really. This actually, you know what? I'm gonna skip that. That's a little more for teachers here. We got a lot of students here. It really is a good day for mathematics, I feel. You know, math's not. Fortunately or unfortunately, depending upon how you feel, math isn't going away. It's 10,000 years from now, we may not be speaking English or driving cars with four wheels, but I'll bet we'll be doing some math. It's just the nature of it. And I really, this again, is a lot of times it is a proud time to be in mathematics, I feel. I really do. Well, I've been in it 40 years, and I'm more pumped about it than I've ever been, really. A lot of mystery around mathematics, and I would like to do one last slideshow here to wrap it up. And there's some equations in it. You don't need to know the equations. Don't feel like there's going to be a test on the equations in this, but I just hope that you enjoy this. I call it the mystery of mathematics. thank you. I greatly appreciate you attending. This is Sure.
Anybody have a question for the speaker?
Yeah, go ahead.
Hardy and Eilenberg and others have argued that some of the best mathematics had no utility whatsoever. How do you think mathematics would change if it didn't have utility?
Oh, how would it change if it did?
Would we still study it?
Well, yeah, I think we would. I mean, it motivates a little bit. And I used to have a prof in college that used to say, what I do is so abstract and off, they'll never find an application for it. But you know, it's kind of funny, they tend to find it in the end. And that is why, which I want to just say one thing. This is why pure research sometimes, people don't catch on to its importance. But sometimes these goofy ideas, Boolean algebra was done 85 years before they did the computer, but it's why the whole thing works. And that's why sometimes that just pure research is very worthwhile and is important to society and is a good investment in many times.
All right, well, thank you very
Okay,
much.
yeah, have a good evening.